Okay. May I have your attention? Now we go to our topic 1, and then we discuss about ITI 1100 a little. And you're introducing. I read all of your posts that you had for your introduction, and so we will talk about it later. Okay. So the first chapter of the book, we go as the book says. So I again emphasize, you read the book as much as you can. It is a very fruitful book, fruitful information for computer architecture. And you have seen those two writers, Dr. Hennessy and Dr. Peterson. They've talked about the golden age of computer architecture. They gave you a brief history of what happened during maybe 50, 60 years, during the last 50, 60 years. And then they talked about the future of computer architecture. So it's good to read the book. After the lecture, you could, is it mine? After the lecture, you could go through the book. These slides, as you could see, this layout, they are all from the publisher. So I intentionally didn't change it, so the copyright is from the publisher. And this layout is are my slides. So just to show you that they are from publishers, and it is good that during the slides, at the top right of the slide, it will show you which chapter of the book the slide is related to. So you could follow the book with the slides and with the lecture that I am giving you. So the first chapter is computer abstractions and technology. We will talk about the technology and how technology is improving, how technology is used for designing computer through the abstractions. This is the chapter. Computers are everywhere. The first revolution was agriculture, I guess. The second one was industrial revolution. The third one was information revolution. And the information revolution was due to computers. So computers are everywhere. And the cost of computing improves. It means cost performance improves. Cost going down, performance going up. So the cost performance is improving during the last 50, 60 years, and it has been said in the video that you have seen. Therefore, with the improvement of designs, with the improvement of cost, with the improvement of technology, all of them all together made possible things that we didn't expect maybe 40 years ago. Of course, lots of things happened. Applications which we never thought of that. And sometimes they were showing these things in science fiction movies. You could see it's not available. And you are seeing them in your everyday life. For example, let's bring you some applications. Automobiles. Now we have autonomous driving. We have driver-assisted computing. They will park the automobile somewhere. We have engine maintenance by the computer, exactly. We have, lots of things is happening inside the automobile. If you see science fiction movies, maybe 10 years ago, 30 years ago, they will give you some kind of automobile that they drive themselves and they have control over there. They could have the cameras that they could see the road, the other things. It's happening now. You have cell phones. Everybody now has a cell phone. So with your cell phone, you are connected. You could communicate everywhere you go. Everywhere you are connected, and they are ubiquitous everywhere. You have, for example, another scientific project, Human Genome Project. So we have a very complicated computers that they can calculate and analyze the DNA, and even they try to produce DNAs for living creatures. World Wide Web. So it's from 1990. It has started, and you see it's everywhere, and we have everything through that. Search engines, Google, and artificial intelligence. Nowadays, you have seen ChatGPT. How does it work and what it does? They are all due to computers and the computing power that we have now in our life. These things are happening. Computers are pervasive everywhere. And I told you last time that everywhere in that camera, in that projector, in that router, in this panel, everywhere they are computers. If you look at all of the computings around you, we can categorize them in 4 classes. Why do we go to classes of computers? What does it have for me, for a computer engineering, for computer architecture course? Because we would like to know the design of computers, how to design it. And when there are different classes of computers, then the design requirements would be different. They have so many things in common. They are all computing. They compute. They have software running inside them. It's common. But they also have a specific requirement for each class. The first class that you are all familiar with is personal computers. You have laptops, you have desktop in your home, and this is something that all of us we are using now. It's around 1980, the PC came to the market, and we are using that. In personal computers, the idea is that you have a general purpose machine that could do lots of things for you. You could run different applications. It's a general purpose machine, and the objective, the main criteria for a good personal computer is cost performance. You usually see for the desktops, they are around $1,000. $1,000 would be a very acceptable. They have a very acceptable performance. So this is something that during the last maybe 40 years have been kept. For laptops, 1,500, something like that, they are the cost of a laptop with a good performance. So the competition between the companies is to make a personal computer with a better cost performance. Sometimes they will give you a lower performance computer with a very low cost. You could see some kind of laptops now around $200. And sometimes they will give you a better performance with more cost. So this is the main criteria of the personal computers. At the other side, we have servers. Servers are somehow more powerful than personal computer because they serve, because they have so many users, not just users. For personal computers, this is mine. So I am using that with applications that I have. But when we are talking about servers, it means that there are lots of users, they are using the server. So it should be more powerful for the server. And usually server works in a network. We connect to the server. So they are network based. They have high capacity, high performance, and reliability. The main criteria in the server would be reliability. Because, for example, you assume that, let's say, Visa credit card server is down for 1 second. Just 1 second during the year, in a year. What happens? There would be huge loss for the company. So they need to have a reliable server. No loss, no breakdown. In just maybe a fraction of a second shouldn't be down the server. So in server, the main criteria would be reliability. And therefore, you might have very expensive servers compared to personal computers, but they have a better reliability. Again, as I told you, why do we go to classes? Because when you are going to design a server, you should consider reliability, and you should design for reliability, for performance. And also there are small servers. You might have a server, you bought a computer, a server, for example, putting in your home, putting Linux on that or Windows, and make some applications there and even serve other people's in internet. Yeah, it is a server, but a small server. And to some server like it's the size of a building. So these are two classes. The next class would be supercomputers. So they are computers containing lots of processors and lots of memory, storage. They are, we could say, a server. They are a type of server, but very, very much more powerful than the server. So we are making them separate because we have to, in designing a supercomputer, you should think of how they are connected, the different processing elements, how the storage is designed, and lots of things that you need to consider. So they are high-end scientific. For example, they are used for the very common example we see is weather forecasting. So weather forecasting is a very good example that they need lots of calculation, and they are using supercomputers to that, or genome project that I've told you before. So they are very much powerful. They are very powerful, and they are very niche markets. So those companies who need a supercomputer, they just go for that. Before, maybe 15 years ago, the main supercomputers were in States, US. But nowadays, if you go to top 500, just Google type 500 supercomputers, you could see that there are, at the top rank, there are supercomputers from China, from Japan, and in this industry is they are working on that. It's now more competitive, but it has a very narrow market for it. And the last one, the last class would be embedded. Embedded, as I've told you, it's then when you are using a computing element, not for computing. It's inside a device. For example, this document reader. It has a processor inside. It has a computing element inside. That projector, that touch screen, even this keyboard, the keyboard, it has a computing power inside. It has a microprocessor inside. So in the embedded design, embedded device, again, these kind of computers, these kind of computing devices, they need a different considerations for design the criteria would be, for example, something which would be small, fitting inside there. For example, this is not, nowadays it is like, we do so many things with it, but originally they were not for computing, they were for communications. So it was an embedded design, and they should be usually small, could fit inside. They should be the power consumption should be very low because they are running on the battery. Usually they are the embedded designs. We have so many portable embedded devices, so they run on battery. These are the criteria for designing an embedded class of computer. They are hidden as components of the systems. The power, performance, cost, they are all together inside that device. It depends on the direct. For example, PlayStation. PlayStation is, again, another embedded device because PlayStation is not for computing. It is not a computer. It's not a laptop. But it has a very powerful chip inside, very powerful processor inside. But again, I told you, for example, this keyboard also is an embedded, but the processor inside, maybe it costs 20 cents, something like that. It's a very cheap microprocessor inside. After the PC, around 1980, if you look at the market, you see the rise of smartphones. Smartphones, the market has a rise in market, and the PC is a plateau. It's almost the same during the last, as 2007 to 2018, the 12 years it's shown here. The PC is almost the same always, but the smartphone had a very increase. Cell phones, they had a rise, but due to becoming smartphones are doing the cell phones right now. So we don't go for a cell phone right now. Just we have a smartphone. It does our phone connection. It does our assistant. It has so many things there. So cell phones decreased, and tablet also. Tablet, sometimes they had increasing market, but they are now. It seems that we don't go to tablet. How many of you right now have tablets? Yeah, no, not here. You don't. Here you have laptop, but home you have tablet. Oh, you have tablet. But cell phones, smartphones are getting the market, dominating the market, and you could see here. Again, these things would be different computers, different class of computers. They are in maybe embedded design. The PC is personal computer, and cell phone also embedded. Due to that, we defined two new classes of computers which are coming to market with the invention of cloud computing. For cloud computing, we have servers. We talked about servers, and they are network-based. Then later, the idea of cloud came. It means that when you have something in internet, in cloud, then why don't you use it? Why should I have a very powerful device here, for example, powerful as it is, and I put everything there? So there is a cloud. There is a server, a good server in the cloud. I just need something to connect to that and use that. With this idea, there are two more classes of computer I am showing you. One is personal mobile device. We talked about a smartphone. A smartphone is something like this right now. But with personal mobile device, we mean anything that could help you in your life, in your work. For example, you would put some kind of glass, Google Glass. So you put a smartwatch. A smartwatch is a personal mobile device. It's a wearable technology. You wear it, and then it will help you. So personal mobile devices, what do? They usually have connection, internet connection, and they connect to server, to the cloud. And part of the tasks are done in the device, in the local device, but most of the tasks are done in the cloud. You send your task to cloud and it will calculate for you. So they are usually battery operated, they connect to internet, and they are cheap. They could be cheap in compared to what they do. A smartphone, tablets, glasses, watch, so many things. And at the other side, there are servers, and we have cloud computing. Traditionally, we had data centers that we put servers there. Then, with the invention of clouds, then we have lots of servers and we have virtualization to making a very powerful server for the customers. Before that, we had different servers. Server 1, server 1, server 2. I have given access to this server, for example, for a customer, to the other server for the other. Then we have some kind of virtualization. With the devices that we had, we built a huge server, a virtual server. Then anybody could get whatever he wants. For example, you need a processing power of 2 core, we will give you 2 core. You need 4 core, 4 core. You need 16 gigabyte of memory, then 16 gigabyte. With the cloud, then we change the way data centers work. So the cloud, then the idea of WSC came. Warehouse scale computing. In a warehouse scale computing, there are millions of computers working together, and they build for you a very powerful facility that you could use it for whatever you need based on your requirement. I might get, for example, I go to Amazon and get a 2-core computer with 4 gig memory with 16 gigabyte hard disk. Another person, you might go and get whatever it wants. So warehouse scale computers has arrived, emerged, and we usually use them in cloud computing. You know, we have software as a service, infrastructure as a service, or platform as a service. I don't think we could reach that point. If you haven't heard about that, you could search, Google it, and so forth. But software as a service, it means that, for example, that I am using my phone, it connects to the internet, and the software is there. I have, for example, my spreadsheet in Google Doc. You connect to your Google Doc, you write anything here, but everything would be there. You connect to Google Sheets, so the analysis would be there, but you use your smartphone to use the Google Sheets. Software as a service, and portion of software run on PMD, and the portion run in the cloud. But these two have also arrived, and we could see these kind of computers nowadays. So we have talked about 6 classes of computer. Mainly there are 3: personal, server, and embedded. But again, then we talked about supercomputers, and then we talked about personal mobile devices, and then we talked about cloud computing, which they are coming from those 3. Yes, please.
So if you were to, for example, kind of use, let's say, your personal computer for cloud computing, or like there's software on the cloud, is your computer then only acting as a display?
As a
As a display, like all the work is being done on the cloud?
display and the connect. It connects there. It's a client, as a client. So right now, I am sure that you are using, for example, you use Office 360. So you are using Word there. You don't have Word on your computer. It is in the server, but you are using your Microsoft Word based on the server. So software as a service is a very bright idea with the cloud. It has arrived with the cloud computing. Amazon and Google would be good examples of the warehouse scale computing that you could see. Oh, based on these things that I've told you, what we are going to learn in the course, that is all of the computers, all of the class of computers that we have seen, they are doing computing. They are executing software. We write software for that. We have programming languages for them, writing softwares. And so we should know how these programs that we write, they are translated into machine language which the computer understands. And when it translates to the machine language, then how a computer is executing them. We will go through that. Maybe you got some very basic idea in a digital system, I am not sure. But here we will show you how the software is going to be executed in the computer. There should be an interface between hardware and software. Dr. Hennessy and Dr. Peterson, they've described that very good in their lectures, if you have noticed that. In 1960, IBM generated an instruction set architecture. Before that, we didn't have this kind of architecture. When we wanted to write software, we have to write software exactly for the computer. The computer say, okay, do this with hard-coded to the computer. And then they thought of why do we do that? We make some kind of instruction set, for example, add, subtract, multiply, move, some kind of instructions. So the instructions is the same. I write a program with this instruction, you write, and then when we want to run it in a computer, there is some kind of interpretation, some kind of translation of these instructions to computer, to be executed on computer. And that was a great idea. And before that, and IBM used that, and after that, they've built 5 computers. They were all having the same instruction set, but different architectures. So the hardware-software interface, which would be the instruction set, we will discuss about that. Then we should talk about the performance. In every engineering discussion, every engineering topic, the performance should be there. You just don't do design for unlimited resources. You should design based on the constraints and then assess your design, then measure how the performance of your design. So we will talk about what would be the program performance. Is it going to be a size of the program? For example, we say the less the program is better, the better. We might say, but the speed, the faster the program, the better. Or the power consumption. Nowadays, the power consumption is important. So if you write a program which consumes less power, is better. So there are different criteria for performance. How do we analyze the performance, and how could we improve that? You have a program with this speed. How are you going to make it faster? We will talk about that in terms of computer architecture. and how hardware the designers improve performance. And then we go to parallel processing. I guess we talked about parallel processing last time also, and for modern computing. So these things will form our course. Software hardware interface, how to improve the software, how to improve the design of the hardware to run better software. So what is the performance? I told you, in any engineering, they should have some kind of measuring the performance. We are not living in a world with unlimited resources, so you do whatever you want. No, you have constraints. When you design, you should measure the performance and see how did you do that and what's the result. For performance, we could see them at different levels. Especially, I am talking about the software part now. The first one is algorithm. For example, you want to sort the numbers. You could have bubble sort, quick sort, different algorithms. They have different performances. So one of them would be algorithm. And based on algorithm, usually what we measure is the number of instructions, number of operations that it need to be executed with that algorithm. The other one would be a program language. You write something in C, then it becomes, for example, 2K, and you write something in Python, and it becomes 2.5K. So different programming languages will make different size of the language, different speed of the execution, and we have compilers, the compilers getting our language, a higher level language, and then they compile it to machine code. You know compilers, yeah? You had course for compiler? Or yeah, compilers translate high-level language to machine code, yeah? If you are not familiar, just tell me so I will explain more about this. Okay. Based on the program language and based on the compiler, you get different number of instructions. We can have a very good compiler which tries to optimize the code so it will generate a number of instructions, but another compiler might generate a larger code. Then we have processor for finding the performance. How fast is the processor? How much memory it uses? And the memory system, how fast is the memory? Because the processor needs to get data from the memory. How fast is that? How is the communication between processor and memory? And how fast the execution is executed? The instructions are executed. And we have I/O. When you have a computer, then it will communicate with the real world through the I/O, input-output. For example, we have keyboard, typing in keyboard. In internet, we have a network card, getting data from the internet or sending data. Again, I/O has a role in performance. You should measure the performance of your I/O, of the I/O of the system. So how fast the I/O is. So you see, there are different performance measures from algorithm, from software, number of instructions, from the processor, from memory, I/O, and so on. They have talked a little about this in their videos, in that video also. There are 7 great ideas for computer design in the world of computer architecture, which we mention it, and it has been gained through the 60 years of designing, and the designers worked there. It was actually 8th grade idea. I will show you the 8th one, and but it now in your book is 6th edition. It is 7 ideas. If you look at the 5th edition, it will be 8 ideas. So the first idea would abstraction. Whenever you want to design a complicated system, not a complicated system, any system you would like to design, you don't go through all the details from the bottom and then coming up and building your design. No, you usually start from top. For example, you want to design a, let's say, a camera detecting the cars in the road. I told you that we have now autonomous driving. So one of the components of that would be a camera for detecting the cars, the road, for example, trees in the road, the people. So these things you need to design a system for that. What do? You start from thinking from the whole system. Okay, I am going to have a camera, I need to get the video, then I need to analyze the video, then, for example, I need to do some kind of edge detection, then I need to, after edge detection, I need to understand the objects. Is it car? Is it tree? Is it a human? And so on. So you start thinking of what would be your system, what would be the component of your system. Then you go, okay, this is my edge detection component. For edge detection, what do I need? I need something to, for example, making a Fourier transform, and then I need something to add, subtract, and so on, and then going down one by one. For Fourier transform, you need this kind of computing powers. So for every design, we use some kind of abstraction and hierarchical consideration for our design. And this abstraction had happened for computer architecture and for our software also. For software, you are using some kind of abstraction. You are thinking at the algorithm level, and then algorithm to high-level language, then with lower-level language, and so on. So this is the first idea, great idea, abstraction. And it helped a lot for designing. In the book, they use this symbol for abstraction. It is some kind of abstraction image, painting for abstraction. The next idea, this is some kind of abstraction. You see, in hardware architecture, we have transistor level, we have gate level, RT level, we have ES level, system level. But there are different levels and different abstractions that we use in hardware design. The next one is make the common case fast. You want to build a mobile. This is going to do lots of things. When you want to improve the performance of this, it's better to start from the things that it is doing most of the times. It does lots of things, maybe. For example, it might, I don't know, use the gyroscope of this to use something, sometimes. But the communication, the internet part, you are using lots of times from that. So if you want to improve that, it is better that you make the common case faster, not the whole thing. The one that they are using mostly in the performance of this, you first start with that. Make the common case fast. And it is, you might think, it is a very simple idea. What is that? But it is very important. For example, with this idea, we built cache, memory hierarchy, for example, because the common case was when we wanted to have the data from the local data, which we will talk later. So, and they will use this car symbol for common case, because this is a racing car, and a racing car which is built for speed, you make this fast in compared to, for example, a van, a SUV. You use this racing car to this. So this is the symbol. The next idea would be parallelism. When you want to make something better, you can do it in parallel instead of doing in sequential. I guess we have talked about this last time. And the idea would be this airplane, the symbol, which have different engines working all in parallel, making the airplane to go faster. The next idea was pipelining. If you have a task doing sequentially, you could do it using pipeline idea. For example, no, not this one. Let me put another example. You go to the laundry room. You have a basket of clothes. You want to wash it. So you go to the washer. You put your clothes there. And it takes maybe 40 minutes to wash them. After that, you have to bring it out and put it in the dryer. Again, dryer maybe takes 40 minutes to dry. And then you take them out, put it in the folder, try to fold it and collect it, and then going to your place. The next person is coming when you are starting your washing. When you are done with washing, you go to the dryer. So what does the person do? If let's say that we have one washer, one dryer, and one folder, what does it do? What does the other person do? It starts the washing machine. The washing machine is there, just there, and nothing is nothing. So the next person comes, puts the clothes there, and wash. And at that time, you are drying your clothes. When you are done with that, you go to the folder. So the next person has done with washing. So it brings out the clothes, put in the dryer, and the other one who is coming can use the washing machine. So you are pipelining. You're doing one by one, all together. At one point, you could see that, there are three people, they are doing in parallel. So the pipelining is good. And the symbol would be this pipeline. You do different tasks, 1, 2, 3, 4, 5 tasks together in pipelining. The next idea would be prediction. Yes?
How is pipelining different from parallelism? It just seems like one person goes into the next vacant spot, but you're not doing everything at the same time.
Yes, in parallelism, you have maybe, for example, two washers. You have two washers, then you do the task of the washing in parallel. For example, you have lots of clothes that you could not fit in one machine, so you do it in parallel. But in pipelining, there are different tasks for one data. First wash, then dry, then fold. They are similar, actually. The idea is parallelization, doing, for example, 4 tasks in one together. So this is the idea. The other idea is prediction. What does it mean? Sometimes we need to wait to find out the result of something and then continue. Yes, there are lots of things. This happens. You need to wait. See what would be the result, and based on that, then continue. With prediction, they say that, no, don't wait. Predict. What would be the result? Predict. It might be correct, it might be wrong. But predict and continue. So this is an idea, a very big challenge, big inventions happened from this idea for example, speculative executions. Speculative executions can come from this idea, prediction. The next one would be hierarchy of memories. When you have memories, you know, in computers, we have main memory to store data. And usually they are DRAM. Do you know DRAM? No? Dynamic RAMs, yeah? DRAMs. The DRAMs are slow compared to the processor. The processor is much faster than the DRAM. So we have main memory DRAM. Then the hierarchy of memories, the idea of this, which happened maybe in 1970s, the idea was, okay, you have your DRAM, your main memory with, for example, 1 gig size, then bring a faster memory, a smaller, faster memory, close to the processor so they can communicate together fast. But this is small, this is fast. This is large but slow. You have hierarchical memory, fast and slow, fast and small at the top, then slower and larger, and also coming down. And dependability. I talked about servers, reliability, and you need to have some designs that they are dependable, they are reliable. So how do you do that? The idea was redundancy. If I have 2 pens with me when I go to work somewhere, then if something happened to that, it breaks or it lost, then I have the other one. I have redundant pen, I bring it at work. I have non-stop working. So the idea of redundancy came into the design of the computers, computer architecture. You will have redundant storage. You will have redundant processing elements. But these ideas, when I'm talking about these things, you say, oh, they're simple. Okay, it's abstraction, common case fast, parallelism. But they changed, they improved the computer industry during the last 60 years. The eighth one was designed for Moore's Law. Do you know Moore's Law? Who knows? Yeah. Please. Yeah.
It's a way of, so before all of the, you can say like computers and stuff like that, it was a way to transfer, it was a language, I guess you can say, that would go through with electric currents and
Okay.
Somewhat, which would be, you'd be able to communicate easily.
The Moore's Law for computer design, for chip design. Maybe you are referring to another Moore's Law. Anybody? Yes.
States that the number of transistors double every 2 years.
Every 2 years. Actually, at the beginning, he said every 1.5 years, and then he changed it to the number of transistors in a chip, in a design, doubles every 2 years. It's fantastic. I will show you a graph for that. So what does the idea mean? The idea is saying that, okay, you consider when you are designing something, you are going to make the product maybe in 1 year from now. At that time and 1 year from now, consider the number of transistors has been increased. So you design for that number of transistors, not today transistors. So this was the idea of it. But it's now gone. It's not valid. The Moore's law after 2016 is not valid anymore. So the number of transistors don't double every, not 2 years, not 3 years. I will show you the graph later. So I stop here and I go for the forum that we had for your introduction. When I